The last of the four perspectives is, and we're trying to go kind of broad to narrow, so this is going to be on that narrow end of the spectrum. Michael Wong is a professor and the chair of chemical and biomolecular chemistry and material science and nanoengineering at the George R. Brown School of Engineering at Rice University. Wow, I said that correctly. I'm excited. He's also a professor in the Department of Chemistry, in the Department of Civil and Environmental Engineering, and the Department of Material Science and Nanoengineering. So definitely wins the prize for the smartest guy in the room, no question asked. He's got degrees in training from Caltech, MIT, and the University of California. And by the way, this is as a child, I really did want to go to MIT. I thought MIT was just this amazing brand. And so this is like the closest I've ever been to actually going to MIT. So I'm very honored to be here for that purpose as well. He's been working on catalysts for clean water. He received the Young Innovator Award from MIT. He's received an award from the American Institute of Chemical Engineers in Nanoscale Science and Engineering, an award from the North American Catalyst Society and the Southwest Catalyst Society. And also now he's focused in the research as related to multifunctional nanomaterials in the National Science Foundation funded Nanotechnology Enabled Water Treatment Engineering Research Center. So please welcome Michael Wong.
Can everyone hear me tonight? Fantastic. Well, I really appreciate the opportunity to participate tonight and to share my thoughts with my fellow panelists tonight about the future of water. You know, to build off on the concept of water, and I think one emerging theme that's come out already is just the scale of the water problem. Okay, we're talking about global. We're talking about billions of people. We're talking about geographical differences and the types of waters that we are worried about. And so I'm going to go the opposite. I'm going to talk about the use of something so small that you can't see it, nanotechnology. I'm going to use nanotechnology to treat this global problem of contaminated water. And before my remarks are done, hopefully I can convince some of you that it's an interesting direction to go to, and hopefully we can make some headway in it, okay? I'd like to draw your attention to the screen here and to notice the first four blue colored letters of the center that I'll be speaking quite a bit about today. It's called the Nanotechnology Enabled Water Treatment Center, NEWT. We at Rice, we call ourselves the Newt Center. Clever, I suppose, right? But that really allows us to remind ourselves that the impact of cleaning water is something that will be not only beneficial to human consumption, but also to our environment and to our ecosystem here. So Newt happens to be a nice, catchy aspect to our center here. My pointer is right here. Excellent. Let me go ahead and tell you about the Newt Center itself and tell you a little bit about my role, and then towards the end of my presentation, give you some snapshots of real scientific projects that we are addressing for the aspects of cleaning water. And so really I speak on behalf of the center here, and really the idea is, before I read this vision statement of the Newt Center, I think the way I'd like to think about the problem of contaminated water is the following. As complex and as complicated as it is, it boils down to one simple engineering solution. Take out the stuff that does not belong in water. Simple enough, right? I like to tell my students in my class, water doesn't contain just H2O. Okay? It contains all sorts of inorganic compounds, organic compounds. It contains bugs inside. Some of those things are harmful. Some of those things causes color to show up in the water. Some of those things are actually harmful. And so what is it about those things that are in water that we wish to remove that allows us to not only drink it, but also to apply it for applications that range from agriculture, oil and gas, fracking applications, et cetera. So I'm going to tie that into the vision of Newt. Really, the idea is to enable access to treated waters around the world, and we're thinking visionary ideas here, by developing technologies, but not just any technology, but technologies that we can deploy in a modularized system, meaning small, user-friendly, to be able to generate clean drinking water for communities that are not connected to centralized drinking treatment systems, and also for distributed places where water is being used for in oil and gas industries. For example, frac wells, okay? And so to boil it down in a different way, the two application points is to develop off-grid emergency response drinking water treatment systems through the use of nanotechnology. And by using the same principles, the scales are very different, and the levels of cleaning of the water are very different as well, that we apply the same approach to wastewater reuse. Okay? Can we clean the water that comes out of the fracking wells to be clean enough that we can reuse? Okay? We don't have to clean it to drinking water levels, but to clean it enough so that the water can be reused over and over again. Okay? So a complicated problem like cleaning water does require a team of universities and industrial partners. And shown here is a map of course, the US. And I shall say that Newt is a team of 4 universities, where Rice University is the lead. We're connected to 2 other universities in the southwest part of the United States, ASU over here, UTEP right here, Rice is we are right here, and Yale, way up in the northeast there, comprises the 4 universities that's part of Newt. We're in year 2 now of this 10-year NSF-sponsored center here. But part of the center requires the participation and partnership with industries, and we have the 12 of the companies that have signed up, both from the drinking water industry as well as from the oil and gas industries, and we're continuing to add folks to Newt to be able to help us transition and to translate basic science discoveries and potential technologies into actually real working units that can be deployed out into the field. Okay? I'll say one more thing, which is that we do partner up and have partnerships around the world, a couple of those shown here in Asia, particularly in China, several in Brazil, and several, of course, well, not marked here, but in Europe, because every part of the world has different water issues. And it turns out that the things that we're trying to do here at Rice is something that is of interest around, not only in the US, but around the world. So nano, for this audience here, I won't read the words here, but I'll just remind everyone here what nanotechnology is about. And you might say, well, I suppose I can say many things about nano, but one way to visualize nano is the following. You take a strand of hair, if you have it, pluck it off your head, and take a razor, but instead of cutting it in half sideways, turn your piece of hair this way and slice with your razor this way. If you slice it about 100 times, then whatever is remaining is about nano size. Okay? Very, very thin. That's nano size. You can't see it, but imagine that you could do it. Now you're in the arena of manipulating material where the material is something you can't see. Shown here is just literally a piece of hair, and if you were to slice up that piece of hair 100 times, then you get this nano hair or this nanofiber. Okay? That ability to control the materials through chemistry, physics, even biology are the tools now that's very well established to generate materials that we can use to perhaps clean water. Okay? The proposition is going to be the following, is that there are real working technologies to clean water. You've already heard reverse osmosis, filtration, air stripping, carbon activated absorption. Those are real working technologies, but those are not the silver bullets. You can't apply that to everything and to everywhere. Cost is an issue, accessibility is an issue, and so nano comes in as a way to enhance those current technologies to hopefully make it cheaper, more efficient. But there's a flip side to that. Can we develop game-changing approaches that no one has thought about yet or cannot be done through current technologies. So that's the power and potential of nanotechnologies. Enhance existing technologies and to create new technologies that do not exist on the market. Okay? So this is where Newt comes in. There are many researchers that's part of Newt, and my role within Newt, I'm part of the executive team that manages the different projects. I'm in charge of one specific suite of projects that looks at developing nanomaterials to clean water of particular priority contaminants. And the concept for Newt is the following. If one were to ask me, what does this unit look like and how should we imagine it? Imagine it as a box that contains a stage 1 and a stage 2, where you go from left to right. Dirty water comes in from the left, and it hits a unit here that takes out some part of the dirtiness of the water, okay? Maybe salts. They're not actually harmful for us, but it actually affects the performance of this second stage cleansing part of the unit. And this can involve photocatalysis, can involve filtration, nanofiltration, nanocatalysis, so that at the end of this two-stage process, you go from contaminated water to either drinking water or reclaimed water, okay? So left is bad, right is good. To go from left to right requires us to develop the technologies in between, okay? So with this audience, I'm going to go ahead and share not one, not two, but 3 technologies. How about that? I'm going to go ahead and try to just show you some pictures, some of the things that we're trying to do to whet everyone's appetite about what could be possible. The idea here is to take what we call absorbent materials and to insert into the absorbent material. For example, the material could be a carbon block that you'd find in a Brita water filter, but to infuse that block with nanoparticles of something. Those nanoparticles can be designed to capture certain contaminants. Oh, for example, BPA, those molecules are not so good. Maybe lead, lead's not so good either. Anything you can pick, there's probably a nanomaterial that you can use to grab out those things, okay? The idea here is to not only develop those tiny nanomaterials, but to insert them and infuse them into a carbon block, for example, and then to actually show how long can we run it, how cheaply can we run it, and how often do we need to replace that carbon block. Okay? These are the types of questions that we're trying to study and quantify now. This is one project. And hopefully, if it works, we have a partnership with a company called Amway that said, you know what, if you have a block of material that does what you say it does, and we're going to work with you on this, we're going to go ahead and try to manufacture this. Okay? So that's an example of trying to take something from the lab towards commercialization with industry partnership. Second example is this project number 2, where we take magnetic nanoparticles, okay? Wouldn't it be really nice if we can take a refrigerator magnet, or maybe something a little stronger, put it next to a cup of dirty water, and have all that dirty stuff just go towards that magnet? Simple to use, room temperature, you don't have to cook anything. All you need is a refrigerator magnet. That's where we want to go. Turns out that there's a number of materials that, if you make it nano, they become really magnetic. These are magnetic iron oxide nanoparticles. These are some TEM images. You can't, again, see them this small with your bare eyes, but you have to use a machine called the TEM. And you take these iron oxide nanoparticles that are very magnetic, and you attach things to it that will glom onto your lead, your BPA, your PFOA, your arsenate, all the things that you don't want. Maybe you can have them magnetically removed with iron oxide nanoparticles. Again, going from lab concept to a unit that can be used. In this case here, we're looking at drinking water applications. Okay? Maybe I'll skip this part here, other than to say we can develop nanoparticles that happen to be cube shapes. Did you know that we can make nanoparticles that look like Las Vegas dye? Okay? And we're going to gamble that these particles here, they're very small, can actually remove nitrates from water. Nitrates comes from over-fertilization, and that ends up in the Mississippi River, and then it ends up in the Delta, and leads to algae blooms. But perhaps through nanotechnology, by making these nano-sized cubes that we can break down nitrates into dinitrogen gas. Does it work? Absolutely it does. In reactors this small. Can we make it work this big? Don't know. It's TBA. To be announced, to be determined. Work in progress. And the last part I'll say is that project number 3, which is, let's use light. Light is free. Light is out there, okay? Can we use sunlight to clean up water? And many examples of this has been done out there throughout the world, published in the literature. Photocatalysis is an example of an industrial application of cleaning water. It's expensive. It costs money to turn on the light bulb to clean water. Can we use sunlight? So this is where we're going to take a fiber optic cable that'll be connected to sunlight somehow, and then to coat the surface of this fiber optic cable with nanoparticles that break down nitrates, BPA. Won't break down lead, but it may be able to attract arsenic, for example. These are all the various wonderful pieces and tools that we can possibly use that's available to us at the nano level that we can now upscale again to a unit that, boy, if it does work, it would be fantastic to be able to use sunlight to clean water at large scale, okay? Again, it all boils down to what's going to be the cost and the regenerability and the ease of efficiency and use. We don't want to make something too hard to use either, okay? Everyone in this room would probably be able to use one of these machines, but if we want this to be used in a rural community or at an off-site location where you need a PhD to operate this thing, it ain't going to get used, okay? And these are some of the things that we do have to think about. With that, I'm going to end with my remarks by just saying that there's a lot of things that are happening in the center. I'm very excited to have shared with you just a small fraction of the things that are going on at Rice and with our team. With that, thank you for your attention.